learner, welcome to this video lecture of Module 11 on Semiconductor Devices of the online course on Electricity and Electrical Wiring. This is the second lecture of the Module 11, which is on Semiconductor Diode. In the previous lecture, we have discussed about semiconductor materials, its properties, crystal structure, and different types of semiconductor. In this lecture, we will focus on semiconductor diodes. It includes PN junction diodes, Zener diode, varactor diodes, their operations and characteristics, and in the last we will discuss about the applications of various semiconductor diodes. By the end of this lecture, you will be able to recognize the PN junction diode, its operation, characteristics, and also you will be able to identify different types of diodes, including Zener diode, varactor diodes, along with their applications, etc. With these objectives in the mind, let us begin today's lecture. So, what is semiconductor? In the previous lecture of this module, we have learned that a semiconductor is a material which has electrical conductivity between that of a metal and an insulator. Semiconductors are essential to modern electronics. It forms the basics of devices like diode, transistors, light-emitting diodes, solar cells, both digital and analog integrated circuits, etc. Now we will broadly discuss about diode. So a diode is a basic electronic device made from semiconductor material, and diode, it consists di plus ode. So di means two and ode means electrode. That means the anode and cathode. So physical contact of two electrodes is known as diode, and its important function is it allows the current to flow in only one direction while blocking it in the opposite directions. This property makes diodes essential for rectification, protecting circuits, and controlling its current flow in electronic devices. Diode generally refers as PN junction diode. This device is small in size, cheaper, tough, has higher operating efficiency. It contains one PN junction. The circuit symbol of diode is shown in the figure. Before discussing the diode in detail, let us first try to understand what is a PN junction. When a P-type semiconductor material is connected to an N-type semiconductor, the contact surface is called PN junction. As we know from the previous lecture that the P-type semiconductor contains holes and negatively charged impurity ions, and the N-type semiconductor contains free electrons and positively charged impurity ions. So impurity ions refers to the charged particles that result from the addition of impurities to the semiconductor material. This process is called what? It is called doping. So doping introduces these impurity ions into the semiconductor to modify its electrical properties. When the PN junction is formed, the holes from the P side moves into the N side and combine with the free electrons. Similarly, the free electrons from the N side diffuse into the P side and combine with the holes. Diffusion takes place because they move randomly due to the thermal energy and difference in their concentration. After few recombination of holes and electrons in the junction, a preventive force is set up automatically. This force is called barrier that stops further diffusion. Due to recombination process, the negative acceptor ion in the P side and positive donor ion in the N side remains unaccounted near the junction. The additional holes and electrons trying to diffuse are repelled by these fixed or immobile ions, and further recombination cannot occur. The region containing the acceptor and donor ions but no free electrons and holes is called depletion region. The presence of impurity ions on both sides of the junction cause an electric potential to set up across the junction that opposes the further flow of carriers across the junction, which is known as the junction barrier or potential barrier, which is known as junction or barrier potential. It is symbolized as VB. At room temperature of 300 Kelvin, VB is about 0.3 volt for germanium and 0.7 volt for silicon PN junction. The flow of charge current through the semiconductor material are of two types, namely drift and diffusion current. So diffusion current occurs when charge carriers move from regions of high concentration to regions of low concentration due to random thermal motion. That means electrons move from the N side to the P side and holes move from the P side to the N side. We have already discussed about this diffusion. Now what is drift current? So drift current occurs when charge carriers move under the influence of an electric field. The drift current flows in the direction opposite to the electric field for electrons and in the same direction as the electric field for holes. Now let us see the PN junction when an external DC voltage is connected across the two terminals of a diode. This is known as biasing of a diode. There are two biasing conditions available to a PN junction. They are forward bias and reverse bias. Forward bias PN junction means when the positive terminal of a battery is connected to the P side of the semiconductor and the negative terminal to the N side, the PN junction is said to be in forward biased state. When the PN junction is forward biased, the positively charged holes are repelled from the positive terminal of the battery and are forced to move towards the junction. Similarly, the electrons are repelled from the negative terminal of the battery and flow towards the junction. Because of the application of forward voltage, an electric field is set up which acts against the field due to potential barrier. Therefore, the resultant field is weakened and the potential barrier as well as the thickness of the depletion region is reduced. As a result, more majority carrier crosses the junction where they recombine and movement of electrons and holes continues. A large current flow through the semiconductor, which is called forward current. Thus, the junction offers low resistance in forward bias. There is also present a small amount of current due to minority carriers, which are electrons in P side and holes in N side, that depends on the temperature but almost independent of applied voltage. Now let us move to the reverse biased PN junction. When the negative terminal of the battery is connected to the P side and the positive terminal to the N side, the PN junction is said to be in reverse biased. The holes in the P side and the electrons in the N side are attracted to the negative and positive terminals of the battery respectively. Thus, the majority charge carriers are moved away from the junction, causing the thickness of the depletion region is increased. This increases the potential barrier and offers a high resistance to the flow of charge carriers. Thus, it allows minimum electric current to cross the PN junction. However, a very small amount of current flows in the circuit due to minority carriers. And this current is called reverse saturation current, which is very small and depends on the temperature. In silicon, it is of the order of nanoampere, and in germanium, it is in the order of microampere. So dear learner, now let us move to the VI characteristics of PN junction diode. The graph between the voltage applied across the two terminals, that is anode and cathode, and the current that flows through the PN junction is known as the VI characteristics of PN junction diode. The voltage is taken along x-axis and the current is along y-axis. In the given figure, the DC battery V is connected to the diode through the potentiometer P. It helps in varying the voltage applied to the diode. The milliampere, that is symbolized as MA, measures the current in the circuit, and the voltmeter measures the voltage across the diode. The characteristics can be considered under three heads, namely zero external voltage, forward bias, and reverse bias. So let us first see the zero external voltage. When no external voltage is applied, the potential barrier at the junction does not allow current to flow. Therefore, the circuit current is zero as indicated by the point O in the figure. Forward bias means when the forward bias is applied, the potential barrier is reduced. The current increases very slowly when applied voltage is less than the potential barrier. At some forward voltage, the potential barrier is eliminated and the current starts flowing in the circuit. It increases with increase in the forward voltage and the curve is almost linear. Reverse bias condition. When reverse bias is applied, the potential barrier is increased. As a result, the junction resistance is very high and practically no current flows through the circuit. A very small amount of current called reverse saturation current due to the minority carriers flow in reverse bias. If the reverse voltage is increased continuously, breakdown of the junction occurs, causing a sudden rise of reverse current and a rapid fall of barrier resistance. The breakdown is the voltage at which the current is suddenly increases to a large value. This breakdown can happen in two ways. So number one is Jenner breakdown and the number two is avalanche breakdown. So Jenner breakdown occurs at a low reverse bias voltage, typically below 5 volts. It is caused by a strong electric field in the depletion region. When the reverse voltage across the PN junction becomes large, the electric field in the depletion region becomes very strong. This field is strong enough to pull electrons from their covalent bonds, causing a phenomenon called quantum tunneling, where electrons tunnel through the energy barrier from the valence band to the conduction band. This results in a sudden increase in current. Now, some characteristics of Jenner breakdowns are it occurs at low voltage, primarily observed in Jenner diodes, and current increases sharply once the breakdown occurs. So next, what is avalanche breakdown? In avalanche breakdown, the electrons acquire enough energy to collide with other carriers. This collision breaks covalent bond and more electron-hole pairs are generated, which gives rise to high reverse current. This process is irreversible and damages the diode permanently. It occurs with lightly doped PN junction. In the junction diode, when breakdown occurs below 5 volt, it causes by Jenner effect, and when breakdown voltage is above 5 volt, it is caused by avalanche effect breakdown. When the reverse bias voltage increases, The electric field across the depletion region becomes stronger. High energy electrons that are present in the depletion region collide with the atoms of semiconductors, knocking loose additional electrons and creating electron hole pairs. These new electrons are accelerated by the electric field, causing more collision and further multiplication of charge carriers. This cascading effect leads to a large current, which is known as avalanche breakdown. Some characteristics are: it occurs at high voltage, it can be destructive if not controlled, as it causes large current that can damage the diode. Now, this table shows the difference between the Jenner and avalanche breakdown that occurs in the PN junction diode. Next, we will discuss the topic, that is application of PN junction diode. There are many applications of semiconductor diodes depending on their variations in dopants, semiconductor materials, and manufacturing techniques. The main applications are as rectifier diodes. They can convert AC current into DC current and DC power supply used in the electronic circuits. A single diodes for modulation and demodulation purposes in communication system. And the third application is as Jenner diodes in voltage stabilizing circuits. The next application is as varactor diodes, which is for use in the voltage controlled tuning circuits as found in radio and TV receivers. And next it is in the logic circuit used in computers. So dear learners, after discussing the PN junction diode, let us now go through a small quiz to test our understanding. I hope you were able to answer these questions. Now let us move to the next topic, that is Jenner diode. So a Jenner diode is a special kind of diode. The Jenner diode is used in the reverse bias mode and it allows current to flow in the forward direction as usual, but will always allow it to flow in the reverse direction when the reverse voltage above a certain value is applied. This reverse voltage is called the breakdown voltage, and it is also known as Jenner voltage. We know that when a diode breaks down, two mechanisms takes place, that is one Jenner breakdown and the other is avalanche breakdown. So Jenner breakdown takes place in the Jenner diode, and in this breakdown the covalent bond of the semiconductor atoms breaks down by a strong electric field set up in the depletion region by the reverse voltage. It generates a large number of electrons and holes that continues the reverse saturation current called Jenner current, and it is symbolized as IZ. It is independent of the applied voltage and is limited by the external resistance in the circuit. This process is irreversible and takes place with highly doped PN junction. In a Jenner diode, when a supply across the diode exceeds the breakdown voltage, it acts like a constant voltage source. So it is the circuit symbol of the Jenner diode, and the VI characteristics of curve of the diode is shown in this figure, and this is for the silicon semiconductor material. So now let us move to the another diode, that is called varactor diode. So varactor diode is a PN junction diode whose capacitance is varied by varying the reverse voltage. Varactor diode operates only in the reverse bias. Under reverse bias, the varactor diode acts like a variable capacitor. Varactor diode is also sometimes referred to as varicap diode, tuning diode, variable reactance diode, or variable capacitance diode. This is the symbol of varactor diode. The circuit symbol of the varactor diode is almost similar to the normal PN junction diode, but it has two parallel lines at the cathode side, which represents two conductive plates, and the space between these two parallel lines represents dielectric. The construction of varactor diode is same as that of the PN junction diode. A heavily doped varactor diode has a thin depletion layer, whereas a lightly doped varactor diode has a wide depletion layer. The depletion region formed across the PN junction acts like a dielectric of a capacitor, as it does not allow electric current through it. The p-type and n-type semiconductor acts like the electrodes or conductive plates of the capacitor, which easily allow the electric current to pass through them. Thus, the varactor diode behaves like a normal capacitor. In an unbiased varactor diode, the depletion width is very small, so capacitance is very large. The varactor diode is designed to store electric charge, not to conduct electric current. So, varactor diode should always be operated in the reverse bias. When the reverse voltage is applied, the electrons from N region and the holes from the P region moves away from the junction. As a result, the width of the depletion region increases and the capacitance decreases. The capacitance is inversely proportional to the width of the depletion region and directly proportional to the surface area of the P region and N region. So, the capacitance decreases as the width of the depletion region increases. If the reverse voltage is increased, the width of the depletion region further increases and the capacitance further decreases. On the other hand, if the reverse voltage is reduced, the width of the depletion region decreases and the capacitance increases. So thus we can say that an increase in reverse bias voltage increases the width of the depletion region and decreases the capacitance of the varactor diode. So the reverse bias voltage should be kept at minimum to achieve the large storage charge. Thus the capacitance can be varied by varying the voltage. In a varactor diode, the capacitance is varied when the voltage is varied. So the varactor diode is a variable capacitor. The capacitance of varactor diode is measured in the picofarad range. Now some of the applications of varactor diodes are: number 1, it is used in frequency multiplier. Number 2, varactor diode is used in parametric amplifiers. Number 3, it is used in voltage controlled oscillators. Now this is the graph that represents the characteristics of varactor diode. So dear learner, it is now time for a self-check of what we have learned about this last part of this session. Now please attempt some multiple choice questions to test your understanding. We have come to the end of today's session. In this lecture, we started with the discussion on the PN junction diode, how it operates when external voltage is applied to it. We have seen two types of breakdowns that occur in the PN junction diode. And finally, we have discussed the varactor diode, Zener diode. In the next lecture, we will discuss another semiconductor device that is called transistor. For further reading, you may refer to the following reference materials. Thus, we have come to the end of this video lecture. Thank you.